Okay, we're going to look at some other types of indeterminate forms and see how we can transform them essentially into the form that we need for L'Hopital's rule. If you remember, L'Hopital's rule is of the form 0 over 0 or infinity over infinity, taking the limit. And so basically we have function up top is going to 0 and the function on the bottom is going to 0 as x approaches a or infinity, or we have both functions, becoming unbounded, approaching positive or negative infinity. There are other indeterminate forms. For instance, 0 times infinity is an indeterminate form. You might say 0 times infinity. Well, 0 times anything is 0. Keep in mind we have two functions. One is getting closer to 0, never actually gets to 0, right? And the other function is becoming unbounded. So this function over here on the left, going to 0, is trying to make the product 0. This one, since this is never actually 0, this is getting bigger and bigger. It's trying to make the product really big. So this indeterminate form could be 0, it could be infinity, it could be something in between. The trick in evaluating these types of limits is to basically realize that, say that I've got a product, two functions f and g, and f is going to 0 and g is going to infinity. So there's two ways I can do this. If a function is going to infinity, then its reciprocal, 1 over infinity, is going to 0. And then similarly, if a function's limit is 0, its reciprocal is going to infinity. And so basically I can rewrite, f times g is the same thing as f divided by 1 over g. These are equivalent expressions. In other words, multiplying by g is the same as dividing by 1 over g, the reciprocal. But when I do this, if g were going to infinity, 1 over g would be going to 0. So if f is going to 0, this would be, this 0 over 0 form. On the other hand, in this form, if I divide by the reciprocal of f, 1 over f, if f is going to 0, 1 over f is going to infinity, and I'm this form. So this is the trick, and let me illustrate it in this example here. As x approaches 0 from the positive side, we have a 0 times infinity form, This is going to 0, and this, if you remember the natural log of x we just looked at in the last video, as we approach 0 from the positive side, that's going to negative infinity. Okay, so the form of the limit, I just say, is 0 times infinity. Yeah, it's negative infinity. It's negative infinity, but that's fine. 0 times infinity, it's indeterminate. So this is not L'Hopital's rule form. To get it in L'Hopital rule form, we're going to have to rewrite this like we set up here. And so how are we going to do this? I'm either going to change it to, instead of multiplying by x, I'm going to divide by the reciprocal of x, or divide by the reciprocal of the natural log of x. Which one should I do? Well, think about it. When we use L'Hopital's rule, we're going to find the derivative. Which derivative is easier to find? 1 divided by x or 1 divided by natural log of x? Okay, well, they're both not too difficult to find, but the 1 divided by x is a little bit simpler. And so that's what I'm going to do. I'm going to rewrite this as the limit as x approaches 0 from the positive side, natural log of x divided by the reciprocal of x. Now this, again, I haven't changed anything. X obviously is always greater than 0, but getting closer to 0. But this expression here, natural log of x divided by 1 over x, is the same as x times natural log of x. However, look at the indeterminate form now that we're in. As we approach 0 from the positive side, natural log of x, the top, is going to negative infinity. But 1 over x also is going to infinity. We've got negative infinity over infinity. I guess you can write it that way. It's still indeterminate, but it's now L'Hopital rule form. So by L'Hopital's rule, we'll now apply. I can take the derivative of the top, which is 1 over x, over the derivative of the bottom. And then keep in mind, 1 over x, that is the same thing as x to the negative 1 power. If I take the derivative of x to the negative 1, that's negative x to the negative 2. So that's negative 1 divided by x squared. Okay. Before I proceed any further, let me simplify. this expression. I've got 1 over x divided by this is the same as multiplying by what? The reciprocal. The reciprocal is negative x squared over 1. And I can simplify this down. Right? Positive times negative is negative. This x cancels with one of those, and I just have negative x. That's what it simplifies down to. And what's the limit of negative x as x goes to 0 from the positive side? It's just 0. Okay? So in this case, the limit does indeed turn out to be 0. And as I said, you know, the limit could be 0, it could be infinity, it could be something in between. Okay? But that's what we have to do to manipulate indeterminate forms of that type in order to get it into L'Hopital's rule form. So I want to look at a couple other forms, and again, we're going to be trying to manipulate them so that we get into one of these two forms, and then we can apply L'Hopital's rule. Okay, let's take a look at this indeterminate form. We actually looked at these way back when we were looking at limits. Infinity minus infinity. Again, that's not necessarily 0. You've got two functions that are becoming unbounded, say as x approaches some value. You know, we might have vertical asymptotes, but one can be growing, you know, if we've got a vertical asymptote, one function can be growing much more rapidly than the other, so that the distance between them, right, the difference between them is getting bigger and bigger, going to infinity. Or it could be that they're increasing at a rate where their distance is getting closer and closer to each other, you know, going, so the difference is 0 in that case. Or we can be reaching some other constant. Okay, so it's indeterminate. We don't know. It's not going to be necessarily 0. So the trick here again is to get it into one of these two forms so that L'Hopital's rule can be applied. So that is not a L'Hopital rule form. So what can I do here? Well, I can simply well, let's show that this indeed is infinity minus infinity. As x approaches 1 from the positive side, the natural log of x at 1 is 0, if you remember. And for values greater than 1, the natural log of x is positive. So this ratio is always positive, but natural log of x is going to 0, and so that's going to infinity. And again, 1 divided by x plus 1 is x approaches 1 from the positive side. This difference is going to 0, but it's always positive. 1 divided by a positive. All right, so we've got infinity minus infinity form. So what I'm going to do is simply subtract these two fractions, and to do that I need a common denominator. What's the common denominator of the natural log of x and x minus 1? Well, it's just the product of these two. So for this first fraction, I'll multiply top and bottom by x minus 1. And this fraction I'll multiply top and bottom by the natural log of x. Okay. Now I can subtract the two. And up top I get x minus 1 minus the natural log of x. And in the bottom I get x minus 1 times the natural log of x. Alright, let's see what we have now. If I plug in x equal 1 now, what do I get up here? 1 minus 1 is 0. Natural log of 1 is 0. The top is 0. If I plug in 1 down here, 1 minus 1 is 0. That's 0, 0 times 0. Bunch of zeros. You know, again, this form is 0 over 0. That's what that form is. So now it's in L'Hopital rule form. Right? So what does L'Hopital rule say? Don't forget, you must write the limit here first. Incorrect without the limit. Derivative of the top. Derivative of x is 1. Derivative of 1 is 0. What's the derivative of natural log of x? 1 divided by x. Now down here, what do we have? Well, in order to find the derivative here, what am I going to have to use? I'm going to have to use the product rule, don't I? So I take the derivative of x minus 1, which is x, which is 1, excuse me, derivative of x is 1, times the natural log of x. That gives me natural log of x. And then plus x minus 1 times what? The derivative of natural log of x is 1 over x. X minus 1 times 1 over x, or x minus 1 divided by x. So this was the product rule in going from here to here. Okay, so we use L'Hopital's rule for that. And let me just also note that I want to look at this expression down here for a minute. Just rewrite it. Well, I guess I technically don't even have to rewrite it. I don't know what I'm doing. Okay, well, I'm just going to leave it just like it is. Sorry, that was a waste of time. Because when I plug in x equal 1, what happens? I get something I can evaluate. 1 minus 1 is 0. This thing is 0. Natural log of 1 is 0. And the top is 0. Sorry, I don't get something I can evaluate. I get 0 over 0, right? So this is again in the form 0 over 0. Okay, so what does that mean? It means L'Hopital rule again. So right, I'm going to come over here, and by L'Hopital's rule, hopefully get somewhere here. Now I know where I wanted to rewrite this thing. I was thinking in the correct form because I want to take the derivative of this. I want to rewrite it, and we'll come back to that. Derivative of the top, derivative of 1 is 0. What's the derivative of negative 1 over x? We just did that one. X to the negative 1 is minus x to the negative 2 times a negative. So it's positive x to the negative 2 or negative or 1 over x squared. Sorry, I'm having some difficulties with my derivatives here, or writing down what I'm supposed to be doing here. Natural log of x, the derivative is 1 over x. And then this thing, what I was saying, this is what I wanted to rewrite. X minus 1 divided by x. I can do x divided by x and 1 divided by x, right? So x divided by x is 1 minus 1 divided by x. Now that makes it taking the derivative easier. Derivative of 1 is 0. What's the derivative of negative 1 over x? We just took it up above. It's plus 1 over x squared. Sorry, that was not very smooth of me in that process, but now when I plug in, I get a real number. Not here, I got indeterminate again, but L'Hopital's rule now gives me a real number. If I plug in, what do I get up top when I plug in 1? 1 divided by 1 squared is 1 up top. What do I get down here? 1 divided by 1 is 1. 1 divided by 1 squared, 1 divided by 1, I get 1/2. So in this case, infinity minus infinity equals 1/2. So again, the trick is to get it into L'Hopital rule form. All right, let's take a look at some other types. These indeterminate forms we're going to look at here, the last ones, involve an exponent. And the exponent is a function of x, and the base is a function of x. But as x approaches a or x approaches infinity, in this one we have the base approaching 0 and the exponent approaching 0. Why is that indeterminate? Well, if the base is approaching 0, it's getting closer and closer to 0. 0 to any power is 0, right? So that thing's trying to get close to 0 with the base going to 0. But the exponent, remember, the base is actually never equal to 0. It's just getting closer and closer to 0, right, in the limit process. But the exponent is close to 0. And anything to the 0 power is equal to what? 1. Right, so you've got 1, the base is trying to get it to go to 0. The exponent is trying to get it to go to 1. So there's a battle between those two. The limit could be 0, could be 1, could be something else. Infinity to the 0 power, same thing. Infinity, this power is approaching 0, but it's never ever equal to 0. So assuming it's a positive, approaching 0 from the positive side, you've got something going, the base going to infinity, all right, base getting bigger and bigger for a given exponent, then that thing's just going to infinity, right? It's just getting bigger and bigger. If on the other hand, right, the exponent going to 0, whatever this base is, right, something to the 0 power, getting closer and closer, something to the 0 power, that's approaching 1. And again, we have a battle between these, right? Is it going to infinity or is it going to 1? Here, the base is approaching 1, the exponent is approaching infinity. So, here it depends, of course, something's getting closer and closer to 1, doesn't matter what the exponent is, right? 1 to any power is 1. Now, the exponent's approaching infinity. If this thing is approaching 1 from the positive side, in other words, always greater than 1, then something bigger than 1 to a larger and larger power is going to infinity. So you've got the base trying to make this 1, the exponent trying to make it infinity. If we're approaching 1 from below, it's actually some number less than 1 to the infinity power is going to 0, but then we have the battle between 0 and 1. So these are all indeterminate forms. Now, determinate forms would be like infinity to the infinity power, or 1 to the 0 power, etc. Those would be determinate. So the trick in evaluating these are not L'Hopital rule form. How do we get 0 over 0 or infinity? Well, it sometimes takes a little bit, but the main trick is to use natural logs, right? Use logarithms. I'm going to use natural log, but use logarithms. Not unlike what we did with logarithmic differentiation. So I'm going to use the natural log and use the properties of the limit, properties of a logarithm, to turn the power into a product. So let me show how this works in this one. Now, as x goes to 0 from the positive side of x to the x, so this is an interesting function, x to the x power. Okay, so what do we have here? As x approaches 0, I've got the base going to 0 and the exponent going to 0. Right? That's an indeterminate form, as we talked about up here. The base is trying to make it go to 0, the exponent is trying to make it go to 1. So what I'm going to do is I'm going to let y be the limit as x approaches 0 from the positive side of x to the x. And so what I'm going to do is I'm going to take the natural log of both sides of this expression. Since they're equal, the natural log of y is equal to the natural log of the limit of this expression that we're looking for. Now, I'm going to do something here. I'm going to push the natural log through the limit, or bring the limit outside in a sense. I'm going to rewrite it this way. And why can I do this? Why can I do this? I'm essentially, going back up this way, I'm kind of, pushing the limit inside the log function, going up, or pulling it out. How can I do that? I can only do that for continuous functions. The natural log function is continuous on its domain, and what's its domain? Values of x greater than 0. And we'll take the limit as x approaches 0 from the positive side, so we're always greater than 0, so we can do that. Now, once I do that, what do I have here? I have the natural log of x to the x power. Remember the properties of logarithms? If I have an natural log of an exponential expression, this power comes down, right, and turns into a product. So, and that comes from the rule of exponents, right? When we raise an exponent to an exponent, and that's exactly what logarithms are, they're exponents, we multiply, right? So this becomes the limit as x approaches 0 from the positive side of x times the natural log of x. And now what do we have? Well, this was the example we just did, right? Let me remind you. Right here, limit as x approaches 0 from the positive side of x times the natural log of x. Remember, that was 0 times infinity. So it's still not L'Hopital rule form. We got it in by, dividing by the reciprocal of x, and then it was infinity over infinity form. We can use L'Hopital's rule, and we evaluated it and got 0. And so I'm just going to use this result, but that's what we would have to do here. So I'm going to say that this is equal to 0 from the previous result. Okay, so are we done? Did we find our limit? Well, be careful here. Did I find the limit as x approaches 0 of x to the x? No, that's y. What have I found? The natural log of y. So all this tells me here is that the natural log of y is equal to 0. So if the natural log of y is equal to 0, what is y? What's the power on the base? The base is e, needed to get 0. Sorry. What's the power on the base needed to get y? I'll rephrase that. The power needed to get y is 0, right? And so this is e to the 0 power, or 1. So remember, logarithms are exponents, right? Ln is log base e. So log base e of y equals 0 if what? E to the 0 is equal to y. And e to the 0 is equal to 1, and so y is 1. So the bottom line is, this tells us that our limit, right, y, is our limit is 1. I want to finish with one more involving an exponent, and it's kind of a classic one. So let's take a look at this. Okay. As x goes to infinity, what's the limit of the quantity 1 plus 1 over x raised to the x power? Okay. Well, as x goes to infinity, clearly the exponent is going to infinity. Well, what's happening inside here? 1 over x is going to 0, so this is approaching 1. So the form of this limit is 1 to the infinity. And that's one of our indeterminate forms. As we said, the base is trying to make it go to 1. The exponent here, notice the base is always greater than 1, right? It's never equal to 1. It's always 1 plus a little bit. Since it's greater than 1 and x is going to infinity, the exponent's trying to make it go to infinity. So is the limit 1? Is it infinity? Is it something else? Is there a compromise, so to speak, here? Well, remember what we're going to do. We're going to just say, let this be equal to y. And then what do we do? We take the natural log of y, and which is the natural log of this stuff. I'm going to go and push the natural log through the limit, as I talked about in the last problem. We can do that. X is going to infinity, and so we're only looking at positive values of x. And then we use this property of logarithms, and this exponent comes down as a multiple of logarithms, as a multiple of the logarithm. Okay. Now, when we look at this form, as x goes to infinity, this is going to infinity. What's this going to? 1 over x is going to 0. This is approaching the natural log of 1. Right, this is approaching what? 0. The natural log of 1 is 0. Infinity times 0, that's an indeterminate form. And so, you remember how we did these, right? The first example in this video, we did one like this. What do? We're going to rewrite this expression to get it in L'Hopital rule form. And the way I'm going to do it is I'm either going to divide by the reciprocal of x, which is 1 over x, or I'm going to divide by the reciprocal of this whole thing. Oh my goodness, that would be a mess to find the derivative of that. Let's just keep it simple, right? Let's divide by the reciprocal of 1 over x. Okay. I haven't changed. This expression is the same as this one, right? Dividing by 1 over x, the reciprocal of x is the same as multiplying by x. But now look at the form. The top is going to 0. What's the bottom going to? 0 as well. And so now we are in L'Hopital rule form. Right? L'Hopital rule form. Alright, now up top, what do I have to use here? What's the derivative of natural log of 1 plus 1 over x? Well, that's the chain rule. That's the chain rule, right? Outer function, natural log. Inner function, 1 plus 1 over x. What's the derivative of the outer function? Natural log of u is what? 1 over u. And what is u, the inner function? 1 plus 1 over x. So it's 1 over 1 plus 1 over x times what? What's the derivative of the inner function? Derivative of 1 is 0. Derivative of 1 over x, we've seen several times, is what? Negative 1 over x squared. Sort of emphasize on multiplying those two together. So that was the chain rule to get the derivative of the top. Now, derivative of the bottom looks just 1 over x. Hey, we know what that is. That's negative 1 divided by x squared again, right? Remember, this is x to the negative 1 power. Derivative of that is negative x to the negative 2. And what do we see here to simplify? Hey, how sweet is that? It's a big mess, but those two are gone away. And what am I left with is I take the limit then as x goes to infinity. I'm just left with this over 1, or just this. And as x goes to infinity, 1 over x is going to 0. And what am I left with? 1 up top and 1 at the bottom. The limit is 1. The limit is 1. Hey, do we have our answer? That was quite a long process. Man, where were we? I kind of got lost. Did we find our limit? Did we find this original limit? Did we find y? No, we found what again? The natural log of y. And so this tells me that the natural log of y is equal to 1. Let's see if we can get this right now. The natural logarithm of y is 1. 1 is the what? The logarithm. 1 is what? The exponent on the base, which is what? E, needed to get y. So y is e to the first power. Y is e. Natural log of e is 1. And so we have this very interesting result, which some of you might have already seen before. The limit as x goes to infinity of 1 plus 1 over x to the x power is actually the number e. In fact, that's a way we can define it. In fact, we can use this expression if you want to approximate the value of e to so many decimal points. Just keep letting x get bigger and bigger in this expression, and you're getting closer and closer to the value of e. In fact, some people use this as a definition for the natural base for the number e. Okay. So again, we had the battle going on. The base was trying to go to 1. The exponent was trying to make this go to infinity, and they compromised. They give you e, which is about 2.7 something. So really cool result here. And so hopefully this second video gives you some idea of the different types of limits that we can encounter, and then get them into a form where L'Hopital's rule comes into play and is helpful.